Everyone, I think, knows ATMs, used ATMs, and our security researchers there have something very interesting to tell us about electronic bank robberies. And because of them, please welcome our two security researchers with a very warm applause.
Are we on? Okay, well, welcome to our little talk here, and thanks for the introduction. Well, as the angel said, I guess everybody knows what an ATM is. It's basically used by people to dispense money from their accounts, either because they live in countries like this one, where you usually don't use like credit cards to pay, or because you don't want to be tracked, right? We're going to tell a little war story here. And that's a case of ATM hacking, a real-life incident, real-world incident that occurred this year. And you want to remember this number here, because that's how you enable the hacked system in case it's infected. And I'm going to hand over to my co-speaker here to tell you about the first few things here.
Yeah, okay. So let's just have a quick look. What do we have in a cash machine? So, of course, we have a safe. That's where we want to get in. There's the money we want to spend. So, of course, we have just a normal computer. It's like a desktop computer. Mostly it's running a normal operating system. Most likely it's Windows XP. And with just a few different manufacturers that built the teller machines. And yes, we as user, we use a common user interface. It's just a screen. Most likely it's a touch screen. Or we have then the EPP number pad where we put the PIN number for our card.
One thing I'd like to add to this slide. What's interesting, you see the picture on the right-hand side. That's a photo we took yesterday when we arrived here at Hamburg main station. And it's interesting because this is the state hacked ATMs are usually in before, you know, the bad guys go there and cash out. So, I don't know, maybe this one's is infected too.
Okay, so now, this is not the first ATM hacking, of course. So the most famous one was from Barnaby at the Black Hat in 2010. You see in the screenshot here that this was the user interface of his malware. So from the functionality, it's quite alike, but not as nice.
As advanced, yeah.
Yeah, of course.
Has anybody in the room looked at this Plotus thing by any chance? No.
Well, okay, so of course we had a lot of POS malware, so from mobile terminals, and to steal just sensitive information like the credit card data or payment data or something. And the most famous one this year even was the Plotus malware. Probably you've heard about, quite famous. We had a quick look at Plotus 2, and it was written in .NET, and yeah, it's from the functionality, it's similar the same, but not as advanced. Yeah, so why are we standing here and talking about this case? We had an incident, a bank, they had discovered that they have a lot of empty teller machines, and they started to work to an investigation for themselves, just a little bit of forensics, and it was just limited success. But yeah, they had to do something about it, and they taped up surveillance and improved the monitoring, and they started to discover that yeah, the infection way was just was conducted via a USB stick, and yeah, they get to manage to arrest the guy and to secure this USB stick. And on this stick, we found actually that malware and started to examine that.
Yeah, so to reiterate that before we go on, so what they did was they figured, okay, there's something going on with our ATMs. They improved their like surveillance technology, if you will, and then saw that guy trying to cash out from one of the hacked machines. And then they went there, arrested the guy, and confiscated a USB thumb drive that he was carrying. And that's where we started our analysis. All right. Yeah, do you want to do this one? Yeah.
Okay, so yeah, they plugged in a USB stick. Just they broke a small part of the chassis, so it's just it's PVC, so it's not really hard to break that. And they plugged in a USB device and forced the ATM to reboot. So you can do that by cutting the power off, or just putting down the LAN interface, or just plug it out. So they forced the ATM to reboot, and therefore they forced it to reboot it from the USB device. And what we found on the USB device was just a simple image of a high-rent bootcd, so everyone can just download that. And within that high-rent bootcd, it's just a mini XP running, and you have a folder where you can just put customer executables that will automatically be started when the XP is booted. So, and within this customer section, we just found our malware. So it was a batch script that was called hack.bat. Just very nice. So actually, we thought we had several thoughts that probably this is just a fake, because they just wanted us to examine the wrong file to save some time, because it was just that obvious. You will have a look at the batch script afterwards, so you can see what I mean. So yes, it's just a mini XP. They put it in. You have the hack.bat, and this will actually start the real malware, the so-called ATM exe. And yeah, what we found then, besides the bootable device on a stick, were some very interesting files. They were obviously copied from the infected ATM teller machines. Because we can tell that because there were 3 different ones that we found there. And it was very interesting which kind of data were copied from the ATMs. So we found data like system data, like for example the software hive key. But moreover, we found, of course, a lot of files that have cash data, credit card data, payment data, something like that, from each of the infected teller machines. And yeah, of course, we have our ATM exe, the file that was really interesting. And yeah, we take a quick look at the hack.bat script. So you see it's very user-friendly, because they implemented a lot of very interesting switches. So we see right at the top that he begins to copy the software hive key of the infected machines. And at first, he's checking if the system probably is already hacked, or if he has to do it. And yeah, the switches you can see here, they are implemented. So yeah, the most used one is, of course, hack. But we see otherwise we have some functionality like clear log files or get the log files. So this is the part where he copies really interesting data from the teller machines. Of course, the question is, why does he do that? We come to that later. And yeah, it's also has got a functionality on it that he can cover his tracks, so you can clear all files of the malware and just remove it also. Yeah, so a little bit more about our installer of the ATM exe.
Yeah, thanks. So, I mean, of course, we were curious. Now that we know how the system gets infected, you know, you insert this USB drive, force a reboot, and then the bat script runs. we were curious, how does the actual cash out process work? How do you get money out of the thing, right? So what we did was we took this ATM exe file, the executable, and reverse engineered that to recover the functionality. And the next couple of slides talk about what we found in this executable. So first of all, the ATM exe is a UPX packed thing. UPX is one of the standard packers. You can easily unpack the original code again. And then we came across an interesting fact. So we unpacked it, loaded it up into our analysis tools, like what you see on the right-hand side. It's a little blurred, but we hope you can still read it. Is IDA Pro, that probably many of you are familiar with, one of the state-of-the-art disassemblers. So we loaded that file up into IDA Pro, took a look at the code, and then we discovered something interesting. We discovered that the original executable contains a resource. So if you're a little bit familiar with the PE format, the executable file format on Windows systems, you might know that there are containers that you can use to store additional data or attach data to a binary. They're called resources. So this binary had a resource, and there was some encrypted data in there, which turned out to be a DLL that contains the actual malicious functionality. And the interesting thing is that this resource is XOR encrypted. Now, XOR is not a particularly strong encryption scheme, but nevertheless, if the key is long enough, like 4 bytes in this case, I mean, you can still probably brute force it, but anyhow, so we figured that every executable that's deployed onto an ATM has the resource encrypted with a key that's derived from the, what's it called again? We have it on the slide, with the volume serial, which is an ID that's assigned to a hard drive when it's formatted by the operating system. That means that every executable that's deployed onto an ATM is tailored specifically for this ATM. So it's not mass malware that you can install on any ATM. Each executable only runs on one very specific ATM, and that's interesting. So, I mean, of course, that raises the question, how do they get this ID in the first place? How do they create this binary with the encrypted resource? Where do they get the volume serials from, right? And there are basically 2 options. I mean, we don't have the answer to these questions, but there are only two options. One is they go to the ATMs the first time and run their stuff and extract the volume serial ID from the system, then go home, prepare the malware, and then come back to infect the system, which seems kind of risky, because if you get caught while doing this, well then you lose something. The other option is, well, we leave that to your imagination. Yeah, so what we did, what you see here on the right-hand side is some code that is executed after the decryption process, after the XOR decryption of the resource. And if you look closely enough, you can see in the first basic block up there, it checks if the first byte of the decrypted data is an M, and then the next one checks if the next byte, the second byte, is a Z, which is part of the PE file header, MZ header, okay? So we figured, okay, this is probably an executable, and that's how we recovered the original code. We assumed that this is an executable, and then you can call it a known plain text attack or something like that. We reverted the XOR encryption and recovered the DLL. And after this happened, of course, the dropper runs some checksumming code to verify that the extracted and decrypted code is actually the DLL it wants to run, the malicious DLL. Okay? So after we recovered this malicious DLL, we took a closer look at that one. And it's dropped into this path up there under the system directory, and the value in squared brackets over there is again derived from the volume ID. So if you come across one of these DLLs, you can take a look at the file name, and that's linked to the ATM it's supposed to run on because of this naming scheme here, right? So that's how, and of course, I mean, you can all see all of that in the code. The second value, the XOR value over there, is hard-coded. That's how we figured, okay, this sample was supposed to run on an ATM with this volume ID. And Then we came across something else, something that's as interesting. This DLL, or the malware in general, writes a log file. It writes a log file and stores this on the USB drive that's used for the infection process, okay? And that's pretty verbose. If you look at this, again, it's, we have to apologize that it's a little blurred, but you can see it's basically what's executed when the batch script runs, right? There is a file name up there, if you can see that, 978, blah, 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 DLL, and some others. And surprisingly, this log file contained information about 3 other infections that took place. So let me switch to the next slide. With that information, we could say, okay, we have information that these guys infected at least 4 ATMs, the ones where we had the DLL for, and then these other 3 that we recover from the log file. Log file, again, is XOR encrypted, but the key is hard-coded, so we could recover it from the code and then decrypt the log file and read it. And this is like an abbreviated version, the most interesting lines from the log. And you can see that all these ATMs run, in fact, Windows XP. Yeah.
Yeah, what probably is quite interesting here is that we have information about the 3 different teller machines that were infected with this USB device in clear text, and we have it additionally in this somehow encrypted log file. So the question is, why do we have that twice? Why do we have this log file? And why didn't they remove that files? Because actually for every new infection they have to build up a new exit device which is encrypted with the volume 0 ID from this machine, and they would have enough time to clear that up, but they didn't do it. So furthermore, big question mark, why didn't they?
Yeah. Okay, now in this part we want to talk a little bit more about the actual payload, the malicious code that's executed on the compromised ATM, you know, the interesting bit. Thanks. And what you can see here is a list of some facts that we discovered. Again, this file, the DLL, contains some encrypted resources. This time they're encrypted with this static key that you see up there. So by looking at the code, we obtained this key and could easily recover the resources. And they contained images like the one that you see on the right-hand side up there. Obviously stuff that they want to display on the ATM screen, right? We changed the coloring scheme and some other stuff here a little bit because we don't want to disclose the target here. But yeah, that's what they store in these resources. And another thing that was in there is this sdelete tool from sysinternals. Maybe some of you are familiar with that. That's a publicly available tool for secure file deletion. So, you know, you overwrite the file first with specific byte patterns before you remove it. And they use that to remove forensic artifacts, forensic traces from the system when, for example, when they're uninstalling the malware, because you can also uninstall it from an ATM. But in case this fails for whatever reason, they have some backup code in the malware, some backup secure undelete code that does basically the same stuff. It overwrites the data first and then deletes the file. So it's kind of interesting that they put a lot of effort into covering up their, you know, hiding their traces on the system. And by the way, we will give you a demo in a few minutes and show you the whole process, how you interact with an infected ATM, and you will see the other screens as well. Yeah, then of course for most malware it's important to become persistent on the infected system, because when it reboots for whatever reason you want the malware to automatically load again. And these guys do that by writing the drop DLL into the app init DLL's value in the registry, in the Windows registry. For those of you who are not familiar with this value, you can specify libraries in there that are loaded into every process that starts up. So by this you make sure that the malicious DLL is loaded into every process that starts, well, within the current logon session at least. What you see down there is some decompiled source code, basically the main function of the malware, of the DLL. And what you can see there is that there are several checks running in cache client 1. Cache client is the term for the software that controls the ATM, that's running on the ATM, and controls the dispenser and so on. So it does this check, and if this returns true, it starts some routine. And if some other checks succeed, then it calls some other functions and so on. Basically what's happening here is that the DLL checks the name of the process it's running in, and then depending on this name, it invokes certain functionality. And we believe that by doing this, they implement support for different cache clients. This line down here, running in else's exe, is also interesting because the DLL is also obviously loaded into the, what's else's again, local system, some Windows process, okay? It's also loaded into that one, of course, because of the app init thing. If it's running in this, it doesn't interact with the cache client, with the ATM software at all. The DLL that's running in there is an event processor. For example, if you want to uninstall the software, you basically create an uninstall event, and then the instance that's running in this process here handles the event and removes the file and so on and cleans up all traces.
What was also quite interesting here, and you can see that later on when we discover the malware itself, so they have really something like a development cycle, so it's really professional made up because within the first infections we could find this malicious DLL within this app init hive key, but there was an incident where the forensic team could discover it there because it's quite obvious, you know, that app init DLL key is very famous for any malware that should start at startup, and they improved that. So later on, they just added this malicious DLL to the DLLs which are started just when this cache client is started. So it's also started from a startup, but it's not as loud. So you have to search quite deeper to find it.
Yeah, sorry. How are we on time? How are we doing? How much time do we have left? Okay, plenty of time. Great. So we know how the malware becomes persistent. We know how it makes sure that it runs on the system, so it injects itself and injects this DLL into all these processes. Now, of course, we want to know how to interact with it, because there must be a way of interacting with the malware. What we found out by reverse engineering code is that the DLL that's running in the cache client installs a hook for keyboard events. So whenever you press a key on the keyboard, which in this case is the numpad, this is trapped by the malware and processed. And what they do is they process only number keys for obvious reasons, because that's the only kind of keys you can enter. And if you enter the code that you've seen on the first slide, that's 12-digit code, you activate a hidden menu that allows you to choose the several options that you can use to control the ATM. Let's see. Yeah, so, but they have implemented an additional measure because, you know, it's possible that somebody by accident enters the right 12 digits and then, surprise, this thing pops up and you can dispense all the money from the ATM. Of course, they don't want that to happen. So they have implemented a challenge response scheme. So when you enter the 12-digit code, the first menu allows you to say, okay, present me with a challenge, and then the malware generates a random or like secret code where the scheme to generate it is secret, and you have to enter a response. And that's not easy to crack. So what they do in this case, because of course the poor guy who goes to the ATM to cash out is not the brain behind the whole operation, of course. Right? They're like, you know, they're likely to get arrested. So they probably don't want to transfer the knowledge how to generate the response for the challenge to these people. And maybe you can tell this story about the phone calls.
Yeah, so actually they had a surveillance video where they could monitor just one of the cache guys, which was just currently had entered the secret 12 digits, and you can see on this video that he has already one part of this hack view. And after that, he just took his cell phone and called somebody, and you can see that after that, within that call, he just types another number, and right after that, he starts cashing out the teller machine. So that's exactly this challenge response check he was talking about. So this really proves that they don't leave anything to chance. They want to control which teller machine is cashed out and exactly when and who does the cash out. So this may implicate that they don't trust their own people, do they?
Yeah. So, I mean, we tried to bring you this video where the guy makes a phone call, but I mean, obviously the bank that was targeted here, they're a little concerned about their identity being disclosed, so unfortunately we couldn't get it, but well, you have to trust us on that. That's how they probably do it. Another thing is that these guys already anticipated that somebody would get a copy of the malware and then probably start to reverse engineer it and understand how it works. And of course, the worst thing that can happen is if somebody recovers the challenge response functionality, that code, and then goes to all the hacked ATMs and you know, jackpots them instead of these guys, right? So they figured, okay, we need a means to protect this really important code. And that's not the only part that's protected. There are several pieces that are, you know, critical, so to speak. So this challenge response thing is one of them, and the other parts that are protected is everything that interacts with the cache client. So you would never, by looking at the code, you would never see a direct API call or DLL function call into the cache client's libraries. All of this stuff is protected, and I'm going to talk a little bit more about how they do that. Yeah, it's a little bit hard to put that in, you know, to find the right words for it. We have a picture of that in our minds, but we called it a state machine. So their obfuscation method is basically control flow obfuscation. So, you know, when you look at some code statically, you can see this function is calling that function, and then it's calling that under this condition, and so on. That's the control flow in the code. But if you don't want to disclose that function A is calling function B, you have to put something in between that obfuscates this relationship, okay? And what they did is they implemented a state machine, that's what we call it, and this state machine consumes a buffer, a static buffer that's somewhere in the binary, and performs some computation on the bytes, and the result is the address of the function to call, okay? So at some point you say, state machine, here's a buffer, do your thing, and then the state machine starts computing the address to call. Or that's only one scenario. The other scenario is that you want to compute a certain value. For example, you enter the response for a particular challenge, and then the state machine, with its functions, computes some other value that it compares to the challenge or something. And this computation as well is protected by this state machine. And you can see a little snippet of that on the right-hand side, again, if you can read it. And you can see there's a lot of junk code in there. Those of you who are familiar with like polymorphism, polymorphic malware, or other stuff like that, you will immediately see that some of the functions in there are total garbage. Like, for example, the sub AL, E1, and then, you know, or some values are subtracted from a register first and then added again. So it's basically doing nothing, many of this, right? So this junk code stuff is one method of obfuscation, and the other is what's usually called spaghetti code. You know, it's jumping back and forth and calling subroutines all over the place. And I think it's really hard or next to impossible to reverse engineer that. At least we spent several days, weeks even, and we couldn't really figure out how the state machine works. And that's exactly the purpose, right? But fortunately for us, there was a solution to this. And that's what the little colored bar at the bottom of the slide shows you. Again, this is something that IDA Pro generates for you, this disassembler tool. You can see the blue stuff at the front. That's the real code, the main code of the malware. So all of that lives in the code section and is at the beginning. Then the green stuff here is library functions. Here you have some data. And at the end, there's some code again. And surprisingly, this is the state machine, right? And it's pretty convenient for us that this is somewhere else in the memory layout. So what you can do is you can put a memory breakpoint on this section here, and by doing this, trap every attempt to execute the state machine code. And then when you're in the state machine, you put a memory breakpoint on the original, on the real code up there, and you get the exit point of the state machine, okay? By doing this, you can basically treat the state machine as a black box. You don't care about the calculations at all. You can still reconstruct the relationship between the calling function and the callee. Okay? Unfortunately, we couldn't use this breakpoint method to understand how these value calculations are performed, but well, you can still inspect memory and somehow understand a little bit of that at least. Okay, now we want to demo to you how this thing looks like. Unfortunately, we don't own an ATM that we can infect, but we have a virtual machine here that's running the malware. And we've patched the malware a little bit. I think we didn't tell you. So what's happening is these screens, when you enter the secret code, these screens that you saw on the slides, they're displayed on a second desktop. So on Windows, you can open as many desktops, like virtual desktops, as you want, and then switch back and forth between these desktops. So what's happening is these screens are displayed on a second desktop, and then execution switches over, or the display switches over to this desktop. So you leave the original ATM display and this process alone. You just switch over to your secret menu desktop, and when you're done, you can switch back. That's a little difficult to debug, because when you do that, when you're running in a debugger and you're using breakpoint and stuff, and the malware all of a sudden switches to a second desktop, well, you cannot control the debugger anymore because it's running on the first desktop, right? So we had to patch a few things to make it more convenient for us to demonstrate this, and that's what we want to do now. Can you? Oh, awesome. Okay, so we have this this little Windows XP VM because we want to be accurate, right? And I'm going to start two processes here. One is I have some little batch scripts. One is the one that simulates the malware running in the else's process, and the other one simulates the malware running in the cache client. This one here. And let's just presume, let's just assume that this is showing the standard ATM screen here now. So enter your PIN and stuff like that, okay? So what we're going to do now is we're going to enter the 12-digit secret code that we saw on the first slide. You remember that, right? And if you do that, you're presented with this menu here, and yeah, it's. Do you want to talk about those values? How that's calculated?
Yeah, probably. So the only thing which is hard-coded are the 3 lines at the bottom here, and all of the rest is just generated with the actual amounts they find on this ATM. So the ATMs, they have a lot of log files which they create, and they just save on the hard drive, and within that files. Every payment transaction is noted. So what the malware does is it requests the newest of that files and just pulls the values into that screen, and so the attacker is presented with the actual value of amount of money, and there he can just choose which one he wants to cash out. So just the 100 bills or all of them. This is quite interesting. We took this screen from an ATM which was already attacked, and there you can see that especially or only the $100 cash cassette was cashed out, because yeah, you know how long it takes if you're just cashing out I don't know 100 or 200 dollars or euros, and if you can imagine if you have a whole cassette full of money, that takes a lot of time, and so this is why they most likely just cashed out this cassette with the most valuable input.
Yeah, so what I can do now is I can either press 0 and then I leave that again, and you know, the ATM shows its standard screen again, or I can press 1, and I'm going to do that now just to show you what's happening. And now challenging me with this code here, and I have to enter the response. And yeah, I mean, it's a 6-digit number. The problem is, because we're not running on a real ATM, we cannot really simulate that here. So, I mean, I can enter a number here now, but even if it would be the right one, if it would accept this, we wouldn't be able to go any further because some pieces are missing here. Yeah, unfortunately, let me restart this, or actually, yeah, I'll restart this. There we go again. Yeah, so usually what happens is you press 1. You get the challenge code, you call your HQ, you get the response code, you enter a response code, and then you have access to this second level menu, so to speak, that allows you to actually cash out. Okay? Well, as I've said, we cannot really do that here, so we have to simulate the fact that we're authenticated, that we entered the right response code. And for that, we patched a little bit in this DLL. Unfortunately, we have to wait for 3 minutes now because there is a timeout. They implemented the timeout as a measure to not leave this screen open when something happens. The guy has to run off or something because police is coming or something, right? Then you don't want to leave this on the screen. So they implemented a timer that fires after 3 minutes, and then after 3 minutes, this window is closed. We patched this timer that after 3 minutes, the second layer menu is opened instead, okay? So we have to talk a little bit more until that happens now.
Probably about the version number, because there you can see they name their software, yeah? Typical software style, of course. And yeah, with a 4-digit value number, so they have really a development cycle for this malware, and they really are improving that with nearly every attack they are doing. They collect all facts they have, they improve anti-forensics, and built in a little more of functionality, and yeah, you can really track this changes they made. This development improves.
Yeah. Another thing we can tell you, meanwhile, is that this challenge code is generated from 2 things. Again, we don't know how it's generated. We don't know the algorithm, but we do know the input. And the 2 things that are the input to this algorithm are an ID that's unique to the ATM, or the station, whatever you want to call it, and a random value. So there's some randomness in there. By this, you make sure that even if the same random value is chosen, the codes are different for 2 different ATMs. So the guy has to, in fact, call you and ask for the code, and cannot, just by accident, enter the right thing and then take the money for himself. All right, now would be a good time for the timer to fire. Let's see. Okay, I have another story. The dropper executable, when something goes wrong, they calculate an error message, an error code. Oh, there we go. And this error code is derived from the value 1337. So apparently they think they're lead, right? Which didn't really stop us from reverse engineering their software, but. Okay, so this screen is like what we showed on the second slide, which basically says this terminal is out of order, go to the next one. And when you see this, well, I mean, 2 purposes. One, others who want to dispense money from the ATM, if they see this, they would not touch it and go to another one. But this also tells you that now you can enter another code, which turns out to be the same 12-digit sequence that we already know, to enter the second hidden menu. And I'm going to do that now. And there we go. And this is now the real menu that you can use to control the ATM. Again, you see the first 4 lines show you how much money for the different bills, the different notes is in there. But now you can actually, cash out. You can dispense that money from the machine. So for example, if I press 1, I can hopefully get the 300, what's the currency again? Well, these are things, are dollars. Or if I press 4, I can get the 50s. So let me do that now, and you can pay attention to the purple line at the bottom. So I press 4 now, and it said wait or waiting or something like that, and now it says the command has failed, which is too bad because I wanted the money, but my VM, the emulation is not that good, right?
Still didn't get to manage to really cash out some money from that machine here.
Yeah, that would be nice. So I could now try to cash out 1, 2, 3, 4, and always I get this failure message, but this is where the malware actually interacts with the cache client. It loads, it resolves the libraries that belong to this cache client and then calls the API functions to trigger the dispense functionality. But the other options at the bottom of this screen are also interesting. Let me show you 7 and 8 first. And that's why I have this little window open here. Hope you can see that. So this is my, my network connections, the network devices that are installed. And as she said, every ATM has a persistent network connection to the bank, right? So they can control what's going on and monitor and so on. So probably before you cash out, you want to disable the network entirely. And they can use 7 and 8 to do that. So let me press 7, and you take a look at that window on the right-hand side. You can see that the adapters are disabled now. And now I'm pressing 8 again. Now they're enabled again, right? That's convenient, right? So you can disable and enable the network adapters entirely. If you press 6, you're going back to this mode. And finally, you can also format the system. I mean, obviously, because you want to remove all traces. So if I press 5, you see this little screen that we already know from the slide. They're somewhat cautious here. Again, if you do that, you can either press 0, then you get back to the previous menu, or you can press 9 and confirm that you actually want to format the system. I'm doing that now, and again, it presents you with a challenge, and you have to enter a 6-digit response code. The algorithm that's used to calculate this here is different from the previous one. And I mean, we figured it out somewhat, but funny thing is it doesn't actually format the system, it just uninstalls the malware. So, I mean, I don't know what the right answer to this is now, but if you enter the wrong one, it keeps asking. And interestingly, you cannot get out of the state anymore. So if you don't know the right answer, you're trapped in this. And I mean, after 3 minutes, the out of order thing is displayed again, but if you enter the secret code, you don't have access to the main menu again, you will always end up at this screen. So unless you enter the right code here, well, you locked yourself out. All right, we want to conclude with some speculation about the people behind this. Maybe, obviously, we don't really know who it is, but there are some interesting facts. And after that, we'll open it up for questions and a little Q&A.
Yeah. So what we really can tell for sure that they want to make serious money with that. They put a lot of effort in implementing and investigating, in coding actually. They built up quite a big team to do that. They have apparently different roles that are strictly assigned. So every role is just his part and is only able to do his part. So it's quite separated. For sure, they have to have profound knowledge about the ATMs, so most likely they really had one to test all these features and to really check whether the coding is correct, whether they get any error messages, something like that. So either they robbed one and really reverse engineer the original cache client to derive that malware from it, or they most likely had someone in the inside which was just had developed the original cache client and therefore really knows exactly how this works. how it's possible just to trigger a cash out without entering a valid card, the PIN code, circumvent all these security measures that are implemented here. Yeah, they have quite good development skills, so the code is quite sorted. You see the development cycle, so as they improve, they implement new features, just like the app in a DLL key and stuff, so on. And yeah, at least they are capable of protecting the code against people like him, like us. They are just trying to reverse engineer the malware, and they really try to cover their tracks for forensic investigations. So they made it really hard to get the pieces together to just have a full image of how that finally works together.
All right. Yeah, that was almost the last slide. You guys remember the 12 digits from the first slide, right? So next time, before you dispense some money from an ATM, enter the 12 digits first to make sure that it's not hacked, right? And if it is hacked, then you enter this here, because that uninstalls the malware.
Well, then we do a short Q&A, if it's okay for you. Please, everybody that has a question, please line up on the microphones signed with the numbers, and then we will do a short Q&A from approximately 8 to 10 minutes.
All right, let's start with you.
Yeah, hi. I have two questions. The first question is whether they were gathering PIN codes and no strips to be able to reuse them later on. And the second question is whether the ATM is connected to the internet through the network connection.
I didn't get all of that. Can the others be a little quiet so we have a chance to understand the question? So sorry, can you please repeat?
Yeah. So my first question is whether the PIN codes and the this magnetic strip or any other information linked to the credit card number is gathered by this malware. And the second connection is whether the network connection gives internet access to the ATM.
Yeah, let me answer the first one, and for the second one I'll refer to her. So this one could gather information like credit card stuff and so on, but it doesn't, not this one.
Okay, I really didn't get the second question.
Second question was, can you access the ATMs over the internet? Is there an internet connection?
No, actually they do not have an internet connection, but it is possible to build so far. So we did that in a test where we tested an ATM, and you can use this USB connection where they plugged in the bootable device and just put an UMTS stick there, and yeah, then you have an internet connection, but per default there is none. But we did that, yeah.
Okay, dann machen wir mal dort von der 1.
Hello. Thank you for your talk. I have two short questions. What was the time span between the infection and the cache out? And did the attackers try to intercept card data?
So the second question is the same as the previous one. They don't intercept any card data. They don't gather like credit card information and stuff like that. They only like jackpot, as Barnaby Jack called it, the ATMs. They only dispense money from the ATMs. For the first question, what was the first question again?
What was the time span between the infection and the cache out?
Yeah, how much time is between the infection and the actual cache out?
Here, we discovered that there were only 2 to 3 days. So they could have any time between that, but they really tried to make it short. And of course, they waited for the right time, so right after the recharging, yeah, because that's the point of most money.
Thank you.
Okay, then number 3, please.
Hi, thank you for your talk. A question about the banking security. This being Windows XP, I missed part of code signing and verified publishers and such. Do banks employ these security measures or not?
They do have security measures, but they are all only implemented when the XP is running. Yeah, so they have whitelisting for applications, they have monitoring for the process, and they have an antivirus, and of course something like that.
But in essence, everyone can dump their own software on it and run it. There's no whitelist for signatures or publishers, right?
There is a whitelist. Actually, there is, but that was the point why they did that via a bootable USB stick, because they wrote this DLL just within the system folder, and they have a whitelist for applications, but not for the DLLs which these applications are using. So this.
Yeah, I mean, it goes without saying that you can take measures to make the ATMs more secure, because this is kind of a trivial attack, right? And as you said, everybody could do that, and that's kind of the reason why we're giving this talk, right? It's no use keeping vulnerabilities secret. They should be like talked about openly, and then people can go and fix their problems, right?
Thank you.
Okay.
Okay, do we have a question from IRC or the community out there?
Yes, there was one question coming from IRC, which was how to get on the USB port or printer to reverse printer port to reverse that machine.
Can you repeat the question, please?
Sure. How to get on the USB port or printer port to reverse that machine?
This was just via cutting a hole into the chassis. So this is just this is no metal, this is not a safe, so this is just a plastic, and there you can just cut a hole in it, and then you can actually access this USB port.
Yeah, I mean, they physically damaged the ATM to be able to access the USB port. And then they had to cut the network connection, right? And that triggered a reboot. Yeah. So it's really a trivial attack.
Not that hard.
Okay, the 4, please.
Yes, two-part question, sort of. One, you would think that banking and money would be kind of a high priority thing to secure. Why are they using Windows XP? And the second one is, if there was a time frame of, I think it was 3 days between the two attacks, why don't they realize there's a hole cut into their ATM and like change it out?
Yeah, so that depends on the USB port that they used. One is in the back, so you don't see it, and the other, it's just you can cut that very, very exact, and then they just repaired it afterwards. They just
fixed it.
Yeah, they fixed it. Just And for the first question, the problem in the main cases is that there are hundreds of thousands of teller machines for each bank, and that's just the problem. They are, of course, starting to renew that, but when they're at the end doing that, Windows has already released at least 2 new versions of operating systems, and that's one part of it. And I think if we had Windows 7 here, it wouldn't change a thing. So.
Well, I think, I mean, that's probably a question for the banks that we can't really answer, but as long as they're covered by insurances, right, they don't really have to care, which is, of course, kind of short-sighted, but maybe that's how it works.
Thanks.
Okay, and now the last question from the number 1.
Yeah, thanks. Hi there. I was just curious about this particular ATM model you were framing the picture of. This is, let's say, the state of security in ATM technology, or if it's just, let's say, an example for how to not build an ATM. I mean, are these bad guys simply the first who found out, well, yeah, it's basically that simple, or is it just, let's say, a really bad model they've been exploiting?
Yeah. That is, that all depends on the original cache client. So the teller machines are all the same, but every bank just has an own cash client, its own software, which is really doing the cashing out, and they're all different. And you have to develop the malware exactly for just one cash client, because it won't work on others. And
I mean, sorry, may I? I mean, also speaking about this physical security, I mean, having an easy accessible USB port and booting USB images without any additional security measure. I mean, is this state of the art? Or?
Yeah. So no, it's not. Actually, this has been fixed because there is a whole disk encryption in place now that just prevents this way of attack. But it's not at all teller machines. It's currently implemented. So yes, it's kind of state of the art.
Yeah, great. Thank you.
Okay, then now thank you to our both security researchers. Give them a great and warm applause, please.
Thanks for coming.
Thank you.
Thank you.